All right, so here's lecture 2 of chapter 7, Quantum Theory and Atomic Structure. Now, where we left off, we had a couple of concepts. One was that an atom with one electron around it had that electron orbiting it and had only very specific orbitals available to it. So that going up an orbital required an input of energy, which we had in the case of light, and going down an orbital resulted in the release of energy in the form of light. So, just basics with spectroscopy. We also figured that light is a particle and a wave. Now, this is all, and that electrons can only have certain very specific orbitals. Now, this is all well and good, but there's kind of a little problem with this model of the atom right here. And that problem is, if you have a detector over here that can detect electric fields, then when the electron is over here, you detect a strong negative field here and a strong positive field here. When the electron is over here, you detect nothing. When the electron is over here, you detect a strong negative field here and a strong positive field here. Well, the thing is, though, that this is a wave. And because it's an electromagnetic wave, it's a photon. So if you have a proton and electron, and they're just particles, and the electron is constantly orbiting the proton, then the electron cannot avoid giving off photons, just normally, even if it's in a resting state. And the problem there is that if it gives off photons, then it's giving off energy. And if it gives off energy, well, then it doesn't have as much kinetic energy, and it has to fall further and further towards the proton until it eventually collides. Which means that this specific model is not stable. And because atoms are stable, this specific model has to be wrong. And so we have a conundrum here. We have a conundrum where we know that the electrons have certain specific orbitals and that they are stable in those, or have certain specific orbits and that they are stable in those orbits, but it can't be an orbit like what we're used to seeing with like planets and a star, for example. This is where we come to Louis de Broglie's work. Louis de Broglie. And he had an interesting proposal. His proposal was, well, we know that light is both a wave and a particle. So what if matter is also both a wave and a particle. Now, the thing about being a particle for electrons, that was already demonstrated back in the early 1800s. De Broglie did most of his work around the turn of the 20th century, so late 1800s, early 1900s. Now, electrons were proven to be particles through the oil drop experiment, where that's where we got the fundamental charge, and it turns out that getting a fundamental charge in an oil drop is a matter of taking away electrons. It's a matter of taking away an electron. But the thing about waves, though, is that waves can only have very specific values if they are confined within a certain space. So picture a string like on a guitar or a violin. Okay? Take the string and you pluck it, and you get a certain very specific frequency out of it. You get a certain tone out of it. Now, the reason you get that tone is because the two ends of the string are held in place. And what that means, from the string's perspective, is that whatever waveform this has, all of the waves on the string have to have the ends here and here stable. Otherwise, the wave itself is not stable. So, you can have the string go back and forth like this, where it goes there and there, where it goes all the way to one side, all the way to the other side. That gives you a stable pitch. Another stable pitch is where you get something like this, where what you have looks basically like a sinusoidal wave, where you have one full wavelength. And then, of course, there are other ways to get it. And one of the things to notice about all of these stable waves is not just that they have the ends in place, but also that the wave itself crosses, but also that if you draw a line here, right in the middle, where the string was in its resting state, you end up getting the wave passing through that line. You end up getting the wave passing through that line either 0 times, 1, 2, or 3 times, and you can go on it and do that more and more. These places where the wave passes where it was before, these are called nodes. the nodes are actually going to be very important later when we talk about the shapes of the orbitals that electrons are stable in. But for right now, just put that in the back of your mind. Now, if electrons are waves and electrons have nodes, then if electrons are waves, then they therefore have wavelengths. So what is the wavelength of a particle, specifically of an electron? Well, in 1905, Albert Einstein published a lot of really groundbreaking research on the nature of energy and the nature of gravity. And one of the things that came out of his 1905 papers was a conversion factor, where energy, which is, let me remind you, the ability to move something, is equal to mass, which is the ability of something to resist a change in its motion, times the speed of light squared. So that what we remember from our last lecture is that the energy of a photon is equal to Planck's constant times nu, which is its frequency, and nu can be broken down further into Planck's constant times the speed of light in a vacuum divided by lambda, which is the wavelength. Now, we can combine these two so that mc squared is equal to hc over lambda. Then we can then from there we can flip these on the top. We can flip these over so that our wavelength goes on the top, and then this comes over here. So what we end up with there is that the wavelength of a photon is equal to h over, now when we move this over here, the h and c here end up on the other side of a fraction from the m and c here. So this speed of light, c, cancels out with one of these, and these two end up on the bottom. There's a little bit of an issue when we're talking about photons, in that photons don't actually have mass. So nothing really has mass unless it can stop or be stable. But photons always have the same speed. So the way to think about this is not so much that it has mass, but rather that it has momentum. Momentum is given the Greek letter rho. I don't know why, and also the Greek letter rho happens to look like a P. The thing is, though, that this relationship is true with any wave, and this is true with any with any set of energy and any set of matter. So we can convert this and make it more general, where the wavelength equals Planck's constant over the mass of an object times that object's velocity. Now, velocity here, I'm using the English letter V. This is the Greek letter nu, so they are in fact different. This, again, represents frequency. This represents velocity. We call this wavelength the de Broglie wavelength. With the de Broglie wavelength, literally anything, all matter has de Broglie wavelengths. Electrons have them. You can calculate the de Broglie wavelength for a proton, for a neutron, for an atom. You can calculate the de Broglie wavelength for a molecule. You could calculate the de Broglie wavelength for this eraser. You can calculate the de Broglie wavelength for a celestial object, for a planet, or a star, or a galaxy. The thing is, though, that because the de Broglie wavelength gets smaller, that as the de Broglie wavelength gets smaller, the less like a wave that the object actually behaves. And the de Broglie wavelength gets smaller as the thing speeds up, and it also gets smaller as the mass increases. So the more mass something has, the smaller its de Broglie wavelength. This is the reason why everyday objects don't seem to behave like waves. This eraser doesn't behave like a wave because its de Broglie wavelength is so small that its de Broglie wavelength is far smaller than the radius of a proton. And so, with this assumption, we can calculate the de Broglie wavelength of an electron. And with the de Broglie wavelength of an electron, okay, the reason that matters is because if the electron behaves as a wave and it is bound inside an atom, then it is also held in place. But instead of being held in place like a string at two ends, it's held in place by the positive charge of the protons at the center of the atom. And so rather than describing where the electron is at a given point in time, it is often more useful to think of the electron as a wave that takes up a certain volume that's centered around the atomic nucleus. And that the reason that the de Broglie wavelength of an electron really matters a lot is because the electron, even though the electron is not held in place by like a literal string, it is sort of held in place by the fact that it has to orbit one or more protons when it is in by the fact that it has to orbit one or more protons when it is part of an atom. So the electron is attracted to the protons and is also and is bound by them. And is also bound by them. And that is where we come back to these waves. Now, if you draw a wave One of the things that you'll notice is that you get these nodes every 1/2 wavelength. You get these nodes every 1/2 wavelength. And in the example of the string, you have to have nodes at both of the ends. So we've got this situation where there is a length that has bounds on it, and the wave is only stable as long as some whole number multiple, that's n for number, as long as some whole number multiple of 1/2 of the wavelength fits within the distance that's set out for it. So here, this is like going from here to here. That's this segment stretched out to this. So this is stable with 1/2 of the wavelength. This one has a full wave in it. That's stable with 1 wavelength. This has 1 and 1/2 wavelengths, so that's 3/2 lambda. And this one, we've got 1 wavelength, we've got 2 wavelengths, 2 lambda. Now, in the example of the string, this distance right here, L, does not change. What changes is lambda. So we've got a bunch of different wavelengths that are each 1, 2, why did I keep writing 2s? 3, 4. We've got a bunch of different wavelengths that are all stable, but only certain very specific ones. And going from the simple ones with no nodes in between to up to wavelengths that have more and more and more nodes in between, these higher number lambdas that are actually towards the bottom here, because I started writing on them on the top, these higher number lambdas actually take more energy to get to. So we can say here, increasing energy from here to here. This part of the board's getting a little busy, so I'm not going to actually write that down. But what I will say is that with an electron that's bound to 1 or more protons in an atom, we have a similar situation where higher n equals more nodes, and also higher n equals higher internal energy. This number here and this n that I put in this equation, this is literally the same n as in Bohr's equation, where the internal energy of a given state is equal to 2.18 times 10 to the negative 18. I hate you for not abbreviating that. Joules Z for the number of protons in the nucleus divided by n squared. This n here, the number of 1/2 wavelengths of de Broglie wavelengths for the electron that can fit inside a given place in the hydrogen nucleus, that n is literally the same n over here that's in Bohr's equation. So we have that connection to make from here to Bohr. And now we're going to have to take a small break from looking at the orbitals themselves to ask ourselves, how do we figure out the shapes of orbitals? Well, and we're exiting section 7.3 and entering section 7.4 now. Well, with the shapes of orbitals, we come to an interesting well, we come back to Newton very, very briefly. So we started off saying that mechanics are the way that very small discrete things work together, the way that they operate. But there are lots of different ways to put these relations together mathematically. There's the Newtonian Mechanics, where everything is, which is based upon Isaac Newton's work, the laws of motion, all that, and the relationship between power and energy and force and acceleration and velocity. Then there is Lagrangian Mechanics, which was after Newtonian Mechanics, and it's basically the same thing, except that the difference was that Newtonian Mechanics was very basic. Isaac Newton was very, very basic in his treatment of pretty much everything. And a lot of that was due to the fact that he was working with a lot of that was due to the fact that he was working on a very fundamental level. But the thing is that what that meant was he had to use a lot of equations in order to come to an answer for any sort of system that was even mildly complicated. Lagrangian mechanics is a different way of writing the same relationships, but that is really, really good for some systems, particularly for celestial systems. Lagrange was he was an astronomer, so he was constantly looking for new things in the night sky, new things in the solar system, and he wanted to be able to plot their trajectories and see if their orbits were stable, etc. Now, in addition to those two, there was another researcher, an Irishman named Hamilton, who did the same kind of work that Lagrange did. Well, by which I mean he adapted Newton's mechanics to work better on his problems. So he came up with Hamiltonian mechanics. Now, what this turned out to be really good at doing is it turned out to be really good at going from some inputs of a system and giving us the internal energy. and giving us the internal energy of the system. Now, if you'll remember from when we talked about internal energy before, the internal energy of a system is the total kinetic energy and potential energy of the system. Now, when we have an atom, when we have an atom with, for example, one electron, we've got the ground state, where n equals 1. We've got the first excited state, where n equals 2. Got the second excited state, n equals 3, and then, we've got more and more and more. We can plot these as internal energy. When a system goes from one state to another, we can measure the amount of energy that's required to do that by measuring the h nu, or in other words, the energy of a photon that's necessary to make that change. Also, when a system goes down different energy levels, it releases a photon of a particular amount of energy, and we can measure that also. So Hamiltonian Mechanics was really, really good at doing this, at going from an input and giving us an internal energy. Lagrangian Mechanics is really useful. I've never used Lagrangian Mechanics, but from what I've read about it, it looks like it's really useful for any system where you can look at how the system is currently and then predict how it will play out in the future. But the thing is that with an atom, atoms are too small for us to be able to see this. We can't get a telescope and, it's not like with a celestial system where we can get a telescope and look at where the planets are. No, so all we really have to investigate this is this change in energy level. Okay, that's not all we have, but that's a really big part of it. And so having a way to calculate what each of these energy levels should be, what each of these internal energies should be, would also give us a way to calculate what their change should be. And so, therefore, we can use that to compare different models for how an atom is set up in order to figure out where the electrons are at any given time. So, we're going with Hamiltonians. Now, with Hamiltonians, what we have is the Hamiltonian operator, h hat. We multiply it by the wave function of the system in question. So, and that gives us the wave function times a certain amount of energy. The little upside down V here on the H is called a hat. What it means is that this H represents not a variable, but an operator. It's like if you took something, it's like if you had a way of saying, this is my operator, and this operator means +4. And so then you did this, and you had, I don't know, 18 over here. Well, in this, operating on 18 gives us 22. Okay, and then you have this, and you have, let's put another number in there. let's put 483.12. Well, PL hat, because PL hat is defined as just being something plus 4. So we take this, we add 4 to it, and we get 487.12. Okay, so that's all that the bracket up here means. It just means that this is an operator of some kind. You can, put a bracket over it and then define what your operator is. So here we have h hat, the Hamiltonian, times the wave function, and that gives us an answer, which is the internal energy times the wave function. It's not h hat times wave function, it's h hat operating on the wave function. That gives us the internal energy times the wave function. So, what does the internal energy itself break down to? Well, it breaks down to breaks down to two parts: the kinetic energy and the potential. Now, I'm using K here to represent kinetic energy. In the book, they use T, and a lot of other places they also use T. I used K to represent kinetic energy when we talked about kinetic energy in the chapter on enthalpy, so I'm just trying to be consistent with what I did before. Now, this gives us a set of constants times the wave function, except that the wave function gets integrated over three different sets of coordinates. I'm just going to use x, y, and z. So that's dx squared, dy squared, dz squared. Yeah, so the wave function gets integrated over three different sets of coordinates, and it's multiplied by a constant. Meanwhile, this here, the potential energy, ends up being if you're talking about the electrons in an atom, so what things we're interested in for chemistry, this is essentially the electric and magnetic forces between the atomic nuclei and the electrons, and each other, and the atomic nuclei and each other. And the wave function is just your model for everything that goes in all of here. The wave function contains your probability field for where the electrons are going to be. You actually get that by multiplying the wave function by its complex conjugate, which is almost the same thing, but not exactly the same thing. So that's almost the same thing as squaring it, but not exactly the same thing as squaring it. It has the momentum of all of the particles. It has the masses of all of the particles. It has the charges of all the particles. It has everything in it, basically. And that ends up making this the most complex part of the whole equation. So this part is based upon fairly well understood physics. So this part basically doesn't change. This part right here, the internal energy, is what we use to compare to our experimental data. And then the wave function, that is what we input into it. This is the thing that where we figure out what we think it is, and we put it in, and we see if we're right by seeing if the internal energies that we get out of the equation actually matches what we think it is. So that's the wave function. Now, insofar as the wave functions for the that sorry, I'm thinking back to when I was in grad school. My P-Chem professor wrote this on the board on the first day and said, "Yep, this is the equation that we write on the board and tell the grad students that it's the most important equation ever, just to mess with them." No, it is really important, but it's also really hard to use. Anyway, with the wave functions, the wave functions matter a lot in terms of bonding and chemical reactions, because what they affect is where the electrons actually are when all of this stuff is going on. And because the chemical reactions have to do with the electrons in the highest energy orbitals usually, or the highest energy orbitals that do not yet have electrons in them, usually, that ends up being a big deal. So the shapes of these orbitals actually do matter. And so that's what we end up poking and prodding with and trying to see if we can get something right. And here I need to, so as a result of that, things like the movements of the atomic nuclei are things that hypothetically you should take into account, but in reality, as compared to what the electrons do, the movements of the nuclei are not as big a deal for figuring out the Hamiltonian. And so as a result, we're just going to ignore that. Now, here's where I have to warn you about something. And that something is the shapes of the orbitals that are given in the textbook. In physics, there's the two-body problem, where you've got two objects and they're interacting somehow. Maybe they're interacting through the electric force. Maybe they're interacting through gravitation. Maybe they are quantum mechanical particles that are interacting through all of the various ways that quantum mechanical particles can interact. Whatever. Two things that are interacting. Well, there are algebraic ways to figure out how the system can interact and be stable. You can go through and systematically figure out every single way in which that system can be stable. A planet and a moon orbiting the planet, if there's nothing else in the system, you can calculate every way that can possibly be stable. But when you add a third body to it, well, then there isn't yet, then you end up with a different type of problem, what the physicists call the many-body problem. With a many-body problem, 3 or more things interacting at the same time, there isn't yet a fully systematic algebraic way to just figure out what all of the stable states of the system are. You can't do it. And so what we end up with instead is we end up with, and when you're dealing with celestial systems, when you're dealing with a solar system, for example, that's not really as big of a deal, because a solar system, you can look at where everything is in the solar system and how it's moving, and then you can figure out if that is stable. And that's much easier to do. But with quantum mechanics, everything is so small that we can't look at it that easily. So we end up having to come up with what the stable states actually are. But we can only do that for a two-body problem. So an atom that has one electron on it, total, we can calculate out exactly what all of the stable wave functions are. We can calculate out exactly what every one of those stable orbitals is. But once we introduce a second electron, those initial sets of calculations become less accurate. And as we add more electrons to the atom, those initial orbitals become even less and less accurate. And so the way that quantum mechanical calculations are done now is that basically new orbitals are generated in a very systematic way, and then they are combined with each other to try to make something that comes close to reality, and then it's a series of guessing and checking, an awful lot of them, until we come up with something that is accurate. Now, the pictures of orbitals that are given in the book are the pictures of what the orbitals would look like on a hydrogen atom. If you took a hydrogen atom and you excited its one electron into a particular orbital, this is the shape of that orbital. And so they are technically correct, but by the time you get down to an atom that has f orbitals in its ground state, that atom already has 56 or 57 electrons plus the nucleus. So you're dealing with a 57 body problem or a 58 body problem. So those orbitals cannot be figured out exactly. We can come very extremely close, but we don't have it exact. So be wary of that. Now, anyway, so this is all well and good. This is all well and good, and let us just put a little pin in there, and let's talk about different kinds of vibrations. So I gave the example of vibrations before by saying vibrations on a string. I was talking about vibrations on the string. But a string is one-dimensional. So let's say that you don't have a string. Instead, you have a drum. You got a drum, you can beat the drum. Now, beating the drum, you also get vibrations. But these vibrations are not one-dimensional. It's not a string, it's a two-dimensional object. It's the surface of the drum. So you can have the situation where the surface comes up and then the surface goes down. In other words, you can have the situation where the where the wavelength, where the vibrations on the drum have a wavelength of double the size of the drum head. So that this is, I should draw this a little farther over, so that this is n equals 1. It just goes up. Now at n equals 2, where the vibrations have a wavelength that is equal to the size of the drum head, so you got 2 half vibrations, there you start to get the nodes. There you start to get the nodes. Except here, because this is two-dimensional, the nodes end up not being points, but end up being one-dimensional. When we had the string, the nodes were just points. So the string is one-dimensional, the nodes were zero-dimensional. Here, we have something that's vibrating that's two-dimensional, and so therefore the nodes are one-dimensional. So we can have the center going up while the outside along the edge goes down, and then, it flips because it's vibrating. But the thing is that because these nodes are now one-dimensional, they can have a lot of different shapes. So we could have a one-dimensional node also that goes straight across, with one side going up and while the other side is going down. We can also have the situation we've got a node that's going straight across the other way. Because if the nodes are exactly 90 degrees to each other, they don't interfere with each other. So with vibrations that have a wavelength, that have the really long wavelengths and are therefore low in energy, so that n equals 1, we've got one mode of vibration. But with n equals 2, we end up with 3 modes of vibration. So as we go up in energy, as we put more energy into the vibrations, there are more ways that the system can vibrate. Now suppose that we don't have something that's two-dimensional, like the surface of a drum head. Let's say that we have something that's three-dimensional, like, I don't know, an electron orbiting a nucleus. Well, at the ground state, at n equals 1, you've got the nucleus here. You've got your electron orbiting it in a spherical shape. So it's spherical, it's a ball. And there are no nodes. Oh, by the by, when I used the example of the string that's attached to 2 points, the string can't actually move at those 2 points themselves. Those 2 points cannot move at all. So the string only, the vibration has to be between those two. Here, the drum head is attached at the rim of the drum. So that part cannot move at all. The vibrations cannot go past that and still be on the drum head. In the case of an electron orbiting a nucleus, however, there really is no hard outer edge. It's more like the electron is attracted to the nucleus, but the wave function doesn't really stop at any point. So, in principle, the wave function for any given electron covers the entire cosmos. In principle, one of the electrons, every one of the electrons in my wrist right here, in principle, has wave function, their wave functions have some value over on the surface of Mercury. I don't know why I'm pointing that way, or I have no idea if Mercury's that way or not. Um, but but their wave functions have some value all the way over there. Their wave functions have some value that is not 0 that's over in the Andromeda galaxy. Okay, the wave functions just keep going and going and going. It's just that the vast majority is balled up in this one little place. So when we draw the shape of an orbital, what we're drawing is the shape that we get if we want something that contains 95% or so of the wave function. So, and again, wave function and probability of finding it is not, they're related, they're not exactly the same thing, but you do get shapes with that look very similar and that have the same symmetry. So we can think of it as drawing where we have a 95% chance of finding the electron. Anyway, so at the ground state, n equals 1, the ground state for the hydrogen atom, we have a spherical shape. We have a spherical shaped vibration that has no that has no nodes in it. At n equals 2, the next level up, we have, here's our nucleus, we have the spherical shape, and then we have one node, because this is the second level. So that node is another sphere. So we've got the big sphere, and we've got another node within the big sphere. And at this node, the wave function goes to 0. So within this sphere, because, of course it's, it's the surface of a sphere, therefore it is a two-dimensional object. Within this two-dimensional space, within the what would be the surface of that sphere, because it's, the surface itself would be 2D. Anyway, within that surface, the wave function does go to 0. So the probability of finding it there also goes to 0. Of finding the electron there goes to 0. However, just like with here, where the node can have different shapes, the nodes here can also have different shapes. So we can have a node that is a flat plane and has two lobes going above and below it. We can have a node that is a flat plane going this way and have lobes going above and below it. And we can have a node that is a flat plane that, is coming that's in the plane of the board. So we've got a node coming out at us and another node behind it. Let me darken that and let me make it look like this is just the edge of the thing. And we've got the other lobe coming behind it. So this gives us a scenario now where we have something different to deal with. So in order to now, what I want to say is the shorthand, basically, for how we deal with each of these different types of orbitals is a little bit, well, it's something that you're going to have to figure out and essentially memorize. This first number, the n, is what we call a quantum number. The quantum numbers basically tell us what type of orbital we are looking at when we try to calculate out what the wave function for one or more electrons in that orbital should be. So the quantum numbers include n, which tells us the electron shell, or the energy level, within each of these, I don't want to really call it the energy level. There are lots of instances in which different orbitals in the same electron shell have vastly different internal energies. So N is the electron shell, and then we have the quantum number L, which is we call it the angular momentum quantum number. And what that tells us is, that tells us what type of orbital we're looking for. We can think of it as the shape of the orbital. So this is n equals 1. All of these are n equals 2. Everything here, both of those, are L equals 0. And all three of these are L equals 1. However, the electrons in these three orbitals might be different for an atom that's in a particular molecule because of the way that the bonds are oriented around it. So we need ways to distinguish those. So we have different quantum numbers for those. We have m sub L, which is I believe that's the magnetic direction or magnetic dipole. But the way that we can think of it is which specific orbital the electron is in. So when you have a moving electric field, that moving electric field will generate a magnetic field. That magnetic field has a specific direction based upon how the electric field moves. So when you have an electron that's orbiting in an orbital, that will it will generate a small magnetic field, and that is something that we can measure. So that is what determines which of these shapes the electron is going to be in. So here, m sub L equals -1, m sub L equals 0, or m sub L equals 1, and here m sub L equals 0. I'm going to get into the rules about these in a little bit. However, when we go to the next step up, to n equals 3, we've got now a spherical orbital with 2 spherical nodes. And for these, what we've got is one node here and a second spherical node here. So like that also. And then I don't even know how to go about drawing this other one. I'm going to draw it at an angle here so that it's like that. And what you'll notice here is that the nodes in this level are just the same as the nodes in that level, but with one more spherical node added to it. And you might wonder, well, is it possible to have, another node that's added that isn't spherical? Is it possible to have another node that's added that is perhaps just a flat plane? And the answer is yes. So we can have orbitals that look like this. We've got two nodal planes. So I'm not a very good artist, but just like these can be perpendicular to each other because they're 90 degrees apart, this also has 4 different ways that it can be, where it can be 90 degrees apart. So just pretend like I drew 4 more of them, and you can easily see how 4 lobes coming off the center where the nucleus is right here can be like 90 degrees apart. So there's 4 more of these times 4, and then there's a fifth that is closely related here. That looks something like that, where instead of just having flat planes, we have more of a couple of cones coming off of it. So these are n equals 3, L equals 2, and then M sub L could equal -2, -1, 0, 1, or 2. So at each level of n that we go up, we end up with a vastly increased, a lot more orbitals that the electron can be in as compared to the levels below it. And so, in order to say which of these orbitals a particular electron is in, we need all of these quantum numbers. We need to know, for the electron, we need to know what is n equal to, what is L equal to, and what is M sub L equal to. And there's one more quantum number that we haven't talked about yet. That's M sub S. So M sub L, that's the magnetic field generated by the momentum of the electron in its orbit around the nucleus. M sub S is the magnetic field generated by the electron spinning on its own. Now, electrons are what we call Fermi particles. I think there's some debate as to whether they actually spin or not. It might be that their magnetic field is just something that they happen to have, that they happen to be, just a permanent magnet that also happens to be charged. I don't actually know, but what I do know is that this means that electrons both repel each other and also draw each other closer together. So what this basically means is that a given electron is that when electrons come together in one of these orbitals, they come together with exactly two. One spin, and they spin in directions that are opposite each other, so that their magnetic fields line up. And they end up sticking together like a couple of bar magnets. You put, you got the north end of a bar magnet, south end of a bar magnet. Then you have another bar magnet right next to it, south, north. Their magnetic field lines line up so well and so favorably that they stick together really well, and they're really hard to get apart. Well, electrons can do the same thing, except that because electrons are also negatively charged, you can only get two electrons lining up like this at a time. So in any one of these orbitals, let me change color. In any orbital, we can have up to two electrons, but no more. In fact, two electrons are preferred. See, once a pair of electrons line up like this, any other electrons that try to come in will not experience any of the pull from the magnetic field, because the two electrons already in that orbital, their magnetic fields cancel each other out. If you're over here, you don't feel this at all because you're too far away, and this cancels it out. And because you don't feel that, the only thing other electrons will feel is the electric field, where the negative charge of the electrons are pushing all other electrons away. So we can have up to two electrons in any one of these orbitals, but no more. And because the electrons attract each other through their magnetic fields, having two electrons in any given orbital is far preferable to having just one. In fact, it's so preferable that molecules or atoms that have only one electron in an orbital are called radicals, because just like a radical, does something unexpected, a radical, a half-empty, half-filled orbital will react with anything that it possibly can. And oftentimes it'll react with whatever it happens to come into contact with. So that gives us our last quantum number. Now, the deal with these quantum numbers is that There are certain rules that associated with what numbers these quantum numbers can actually have for an electron. First, n. You have to have at least one half of a wavelength in an orbital. So n has to be a positive whole number. 1, 2, 3, 4, 5, etc. Has to be positive, has to be whole. Why in the world am I writing it up there? N has to be positive and whole. It must be a whole number. So it can be 1, it can be 2, it can be 3, it can be 7. Okay, it has to be a whole number. L has to be a whole number including 0, because L equals 0 is the sphere. So it could be 0, it could be 1, it could be 2, but it cannot be greater than or equal to n. When n equals 1, L can only be 0. When n equals 2, L equals 0. That makes sense. L equals 1. Okay, we have a new set of types of orbitals. With n equals 3, L could be 0, 1, or 2. So it has to be a whole number, including 0. It cannot be greater than n. So it could be a 1, 2, 3, 4, etc. With m sub L, now remember the whole purpose of m sub L is to take one of, is to say which specific orbital within one of the types, which specific orbital the electron is in. So m sub L can have any value from plus L to minus L. Or 0. So if L equals 2, for example, then m sub L could be -2, -1, 0, 1, or 2. But if L equals 1, then it can't be -2 or -1. It can only be these three. And then finally, m sub s, the magnetic field due to electric spin. This can only ever be plus 1/2, or it can be minus 1/2. Now it's plus 1/2 minus 1/2 instead of plus 1 minus 1 due to the fact that these are fermions, and that is different from being bosons. Bosons have whole numbers. You know, 1, 2. Bosons have whole numbers spins. 1, 2, 0, etc. Um, there's something with quantum mechanics where bosons can really crowd into quantum mechanical states, whereas fermions can't. I'm not going to get into it because for our purposes it doesn't matter. But yeah, m sub s can only be plus 1/2 or minus 1/2. Or, in other words, we can abbreviate this as spin up or spin down. Now, one of the things about spin up and spin down is that, one of the things about spin up and spin down is that it's not actually up and down. These are up and down relative to each other. You know, the specific direction that a given electron has a spin up, it can be literally any direction. It could be that way. It could be that way. It could be that way. Or it could be this way, and then the electron gets hit, and suddenly it's that way. You know, the specific, so the specifics of which specific direction is just it's kind of an arbitrary direction, but it's not arbitrary compared to the other electrons in the atom. And it's not arbitrary compared to the other electron in the orbital. So that's why we just abbreviate it as spin up, spin down. So, with that there, let's talk a little bit more about the orbitals themselves and their various different energies. Because these orbitals don't just have, numbers associated with them, we also give them names. So for the spherical orbitals, we call them s orbitals. S for spherical. For the orbitals that are shaped like this, where this is L equals 0, for all of the orbitals L equals 1, like that. So there's some actual geometric term, I think, but I've always just called them the propeller orbitals. Or the p orbitals. Propeller because if you look at really old aircraft that were made in like the 1920s and 30s and stuff that only have 2 blades on the propeller, the p orbitals are shaped kind of like that. Then this kind of orbital where L equals 2, these are the diffuse orbitals, or the d orbitals. I'm going to go into why they're called diffuse orbitals in a bit. Well, no, I'll just go into it now. So I'm drawing this as being about the same size as these. It's actually not. If you put the p orbital here next to this, these orbitals are much bigger. The electron density is much more spread out. Now they're still in the n energy level. They're still in the n equals 3 electron shell. But they're still there because of the symmetry, but their electron density is so greatly spread out that it's actually harder to put electrons in here than it is to go up one more energy level and put the electrons into a spherical orbital. And hence it's called a diffuse orbital. And we're going to talk about that when we go into periodic trends of the atomic orbitals. Now, finally, what happens if you take this and you add a bunch more planes of separation? And you add a bunch more planes. Well, then you get... So, this is basically that cut in half. This is basically that cut in half. You get something that looks like this, cut in half two ways. These are the L equals 3 orbitals, or the F orbitals. If F refers to anything specific, I don't know. Now, in principle, we could keep going up and have more and more complex orbitals. After F, we just name them alphabetically. So the next set up are the G. So the next set with L equals 4 would be the G orbitals. Then with L equals 5 would be the H orbitals, etc. But we're not going to bother with those because for our purposes, this set is going to cover everything that we need. Now, yeah, so d orbitals and f orbitals don't usually get involved in bonding with nonmetals. With metals, d orbitals can sometimes get involved in bonding. F orbitals even then rarely get involved in bonding. So for the most part, what we care about are the p orbitals and the s orbitals. At least for the most part in this class. That's what we're going to care about. That's what we're going to focus on. And one of the things that I want to draw your attention to is something that I'm sure you went over in Chem 170, which is the 8 electron rule. So the 8 electron rule comes from here. How many s orbitals do you have at any given energy level? 1. One orbital. And how many electrons can you therefore fit into an s orbital in any given energy level? Well, 2. And at this point, we're done talking about drums, so I'm just going to go ahead and erase that part. Now, for the p orbitals, how many orbitals do we have at any given energy level? Well, we've got, or at any given electron shell, we've got 3 of them. And how many electrons can we fit? Well, we can fit 2 into each one. We can fit 6 into them total. For most nonmetals, these are the only orbitals that are used in bonding. And this is where we get our 8 electron rule from. If an atom only uses s orbitals and p orbitals from bonding, then its bonds cannot exceed 8 electrons total. Now the diffuse orbitals Well, if L equals 2, then what that means, I erased the M sub L. M sub L can equal -2, -1, 0, 1, or 2. And so here, 1, 2, 3, 4, 5. There are 5 orbitals. And because we can fit 2 electrons into each one, we end up with 10 electrons total. In transition metals, we often talk about the 18 electron rule because transition metals can use the d orbitals in bonding. With f orbitals, L equals 3, which tells us that we can add on two more orbitals beyond this. So we start out with 1 orbital of this type, then 3 orbitals of that type, then 5 orbitals of that type. So each time we go up 1 more type, we can add 2 more. So 7 orbitals here for a total of 14 electrons. The shapes of orbitals are going to be very important. That's going to be important next chapter when we talk about chemical periodicity. It will also be important when we go on to more advanced discussions about bonding. So this is important to know. Also, the quantum numbers of electrons, that is important to know.